Hello everybody, my name is Steve Frey, and today I'm going to present groundwater and surface water forecast evaluation in two contrasting hydrostratigraphic settings within Southern Ontario. I'd like to acknowledge all of my co-authors on this presentation, as well as the contributions from Mark Boone at Quinte Conservation, the Long Point Region Conservation Authority, MECP, who funded the project, the GSC, who initiated the development of the regional modeling platform a number of years ago, as well as the full Quinte team. The objectives of this project are to evaluate the ability of hydrogeosphere to forecast surface water and groundwater conditions in two regions within Southern Ontario that are both prone to drought conditions. The forecast intervals that we're looking at extend over 7 days and 32 days. And it's important to note that this is actually a continuation of the presentation I gave last year, where we talked about the development of the two models being used here and their calibration performance. And now this year, we're going to look at how these models behave when they're put into a forecast application. So the two watershed regions that we're interested in lie in the south of the Southern Ontario model domain, the regional model domain. So that's one in the Long Point region. And then the other lies in the eastern part of the Southern Ontario regional model domain out in the Quinte region. So the models that we're talking about today have both been derived from the regional model that was constructed using hydrogeosphere over the course of the Southern Ontario groundwater project that was run by the GSC. And from that, we carved out two watershed scale models, one for the Long Point region, one for the Quinte region. And we did some more in-depth calibration on those models and evaluated their performance to reproduce historic stream flow and groundwater conditions. And then we put them into forecasting application. And it's important to note that the hydrostratigraphy in both of these models is largely exactly the same as what was constructed for the regional model. So really it's a demonstration of regional model utility for watershed scale forecasting. And one of the advantages, though, of course, when we're doing these smaller watershed scale models as opposed to a larger regional model, is we can put a lot higher level of spatial resolution into the model, which is what you see in the bottom right, which is the discretization over the surface and then the layering propagating through the subsurface. We originally evaluated the surface water flow performance of these models at all of the Water Survey of Canada gauges that lie within the model domains. So here we're looking at, on the left, the surface water gauges that were used for the model calibration in Long Point region, and then similarly the surface water gauges in the Quinte regions that were used in the model. So groundwater calibration was conducted using the PGMN wells that are located within each one of these model domains. So on the left now we're looking at the distribution of wells across the Quinte model, and then on the right we're looking at the distribution of wells across the Long Point model. And the wells that are circled are the wells that we had real-time data feeds provided over the course of the forecasting project. And these were the wells that were used to evaluate the forecast skill. So there was 8 wells in the Quinte model and 3 wells in the Long Point model. So the weather forecasts that were used to drive the hydrogeosphere hydrologic forecasts were obtained from the GEPS version 7 from MSC. That consists of 21 ensemble members, and it's available on a 16-day forward-looking forecast that's produced every 6 hours, and a 32-day forward-looking forecast that's produced every Thursday. And this provides a 44-kilometer spatial resolution. So if you look at the raster map here in this image, you get an idea of the pixel size and the weather forcing relative to the model domains, and it's relatively large pixels relative to the watershed areas. So in observing this, we have to be aware that, in these types of weather forecasts, we're not necessarily able to predict the location of convective precipitation with a lot of accuracy in the summertime. It's a somewhat diffuse perspective on weather conditions, and that may have some implications for some of the simulation and forecast results that we'll look at later. Hydrologic forecast. The hydrologic forecasts were produced using each of the weather forecast ensemble end members, which gave us an ensemble of hydrogeosphere forecasts. That ensemble allows us to bracket the uncertainty as well as predict the median forecast conditions. And we were able to do that for both surface water flows and groundwater heads. The forecasts for the 7-day forward-looking interval were provided on a daily basis, and the forecasts for the 32-day forward-looking interval were provided every Thursday. The skill evaluation extended from June 26, 2021 to December 21st, 2021, which means we had 126 daily weather forecasts and 20 weekly weather forecasts to evaluate for their forecast skill, and that covered the summer and fall time intervals. The way we assess the weather forecast skill was we would take a weather forecast that was produced, say for instance, this time last week, 7 days ago, and we would let 7 days of real time transpire, and then we would look at how the real world conditions then compared at the end of that 7-day real world time interval to the forecast that we provided 7 days ago. And the skill metrics we used for groundwater were linear correlation, root mean square error, and absolute bias. And for surface water, we used the KGE metric, root mean square error, and absolute bias. And the reason we used KGE as opposed to NSE or some of the other variance-based metrics is that KGE actually encompasses elements of linear correlation, variability, and differences in means. So we have a number of different skill targets wrapped up in a single metric. And unlike the NSC metric, KGE is equivalent to the observation of the mean forecast when its value is approximately minus 0.41. So anything really above minus 0.41 with your KGE metric means that your simulation skill is better than the mean of the observed data. So the first forecast we're going to look at is surface water in the Long Point watershed. Panel A at the top shows the KGE metric looking forward over the 7-day forecast interval. For all but 2 stations, the forecast generated by the model did a better job at anticipating future conditions than the mean of the observed flow conditions at that station. And some of these stations were actually very well predicted over the entire 7 days, while others kind of declined. Root mean square error for all but 2 of the stations ranged from about 1 to 10 cubic meters per second over the 7-day forecast interval, and bias tracked around 0 with a slight increase as the forecast interval marched forward. Now it is important to note here with the Quinte model that we weren't simulating the surface water management that occurs within that watershed region. And there are quite a number of dams that are used to control flows during the summer, and their impact were not incorporated into the forecast. So it could be expected that some of the stations that are impacted by upstream water management weren't being captured properly. So I think we could look at this type of a forecast and say this is the watershed in its natural flow state, not a managed flow state. So another aspect to keep in mind is that there's seasonal influences on forecast skill. So using Quinte as an example here and comparing the forecast for the 7-day intervals during the summer, top left, and fall, bottom right, we can see that the forecasts in the fall have a much higher skill for a longer duration than the forecast provided in the summer. And that's true for the KGE, root mean square error, and the bias. So in general, we can definitely say that there's some seasonal differences in the ability to forecast the hydrologic conditions in these watersheds. And this difference that we see could very well be related to the prevalence of convective versus frontal precipitation systems. So convective systems, more localized, less likely to be resolved in a 44 kilometer weather forecast pixel size, whereas some of the frontal systems can likely be better resolved at that resolution. So now we'll move on to groundwater forecast skill, and we'll start with long point. So we have linear correlation, root mean square error, and bias. And now we're looking at the 32-day forecast interval as opposed to the 7. So with the surface water forecasting, the skill tended to degrade pretty quickly by the time we hit 7 days, whereas the groundwater forecasting, we have skill that progresses out well past 7 days, and in some cases, we have forecast skill out at 30 days. And that's identified here. So the linear correlation, even out at 32 days, is above 0 for all 3 of the wells for which we had real-time data feeds at long point. Root mean square error was generally 1 meter or less over the 32-day forecast interval, and the bias tended to bounce within plus or minus half a meter. So now we'll move on to groundwater forecast skill in Quinte. Now we have 8 real-time wells that we're providing as data. So we have a larger assemblage of wells where we can assess the ability to predict the future groundwater conditions. And again, we're looking at a 32-day forecast. Linear correlation for all of the wells really shows good forecast skill out past about 15 days. By about 20 days, we see a couple of wells start to drop off, and there's another well, a third well, that kind of deteriorates by about 25 days. The remaining wells are predictable out to the 32-day end of forecast time point. Root mean square error tends to grow but stays within about 1 meter for all but one of the wells over the 32-day forecast interval, and bias tends to deviate on the plus side, and it extends up to about 1 meter over the 32-day forecast interval. So that we have one outlier well here for sure, where we see something odd going on at around 10 days in terms of the root mean square error. But generally, the groundwater in Quinte is quite predictable as well. In conclusions, we can say that outliers exist for both surface water and groundwater forecast, and those outliers tend to skew the means. Seasonal influences tend to affect the surface water more than groundwater. Fall has better skill than summer. The Long Point region has somewhat higher skill than Quinte for both surface water and groundwater. And if we exclude the outliers, we can say that surface water flow conditions are generally predictable 3 to 5 days in advance, in some cases up to 7 days, and groundwater conditions can be reasonably predicted at 20 plus days in advance. And it seems that the diffuse response of groundwater to spatial variability in precipitation appears to make it less sensitive to coarse resolution weather forecast data as compared to surface water. And with that, I'll thank you for your attention, and I'm happy to answer questions.